Bismillah ar-Rahman ar-Rahim. Last time we started the addition and subtraction in 2's complement. And we said that addition and subtraction are very similar in 2's complement. And therefore we can use the same circuit for both. Almost the same circuit for both. But since we use the range, or since the range of the result is limited in the signed world, okay, we must watch for overflow of result. And we gave an example last time, okay, by adding, when you have 4-bit numbers, okay, when you have 4-bit signed numbers, if you add 0, 1, 1, 1, which corresponds to +7 into its complement, and 0, 1, 1, 1, okay, so you add it twice, you get, if your result is not signed, then you get 1, 1, 1, 0, which is +4, which is 14. So that's correct. But since we are using signed numbers here, notice that we are using a positive number and a positive number. So we're adding 2 positive numbers and we get a negative number. So this must indicate an overflow. Okay, there is an overflow condition here. So when does the overflow happen? Basically, when you add 2 positive numbers and you get a negative number, or when you add 2 negative numbers and you get a positive number. Before I continue the discussion, I would like to talk about 2's complement representation, okay, for a little bit more, okay. So let us assume that we have 3-bit signed representation, okay, 2's complement representation. And I would like to know the range of the numbers. We have talked about the ranges for the sign and magnitude as well as the 1's complement, but we haven't talked about the range for 2's complement. Okay, so the range here, okay, is going to be, let's just enumerate the numbers first and then talk about the range. So for 3-bit, we can count starting from the 0, from 0, okay, this is 0, and then this is followed by 1 plus 2, and then plus 3, and then that's it. That's the maximum positive number that we can get. Okay, so what is the next number that we get is going to be negative, right? So this is 1, 0, 0 is going to be some negative number, okay, because the sign bit is negative. And then 1, 0, 1, and then 1, 1, 0, and then 1, 1, 1. Okay, so let me ask you this. What is the magnitude of this number here? So you have 2 ways of doing this. The first way, okay, is to change it to its positive counterpart. So 1, 1, 1, okay, we have to find its 2's complement, right? 2's complement is going to be 1, 0, 0. So its positive counterpart is +1. So this must be -1. So this is -1. Okay, I'm going to write the decimal value below the number. So this is -1. And then what about this one here? 1, 1, 0. What is the 2's complement? It's going to be 0, 1, 0, right? So this is +2, and this must be -2. Okay. All right. So this is -2. Another way of doing of converting, of finding the value of the number, okay, in decimal, the value of a negative number in decimal straight away without even converting to the positive counterpart, is to note that The most significant bit in 2's complement, so let's say this is a 3-bit. These are the 3-bit of the 2's complement here number. So this is B2, B1, and B0. This bit here has a negative weight. It's a negative 2 to the 2. And this bit has a positive weight of 2 to the 1. And this has a positive weight of 2 to the 0. Okay? So you can right away convert this number here to its decimal value by following this conversion here. Okay, so this is going to be a -4 plus 1, which is -3. Okay, and this one here is going to be exactly -4. Okay, do you see this, guys? I have a feeling that you guys are not following because I don't get any response from you.
It's clear.
Please, guys, when I say something, please reply back, okay? I have a feeling that you're busy with something else. Don't do that, please, okay? I need you to be more active in the lecture, okay? So now let me check your information, your understanding of this. If I want, let's say 5-bit, 2's complement, okay? 2's complement representation. Okay, and I would like to find the value of this number right away using this technique here. What do I do? So this bit has a weight of 1. This bit has a weight of 2. This bit has a weight of 4, 8, and then -16. So the most significant bit always have a negative weight, okay, which is equal to the positive weight if the number is unsigned, okay? I mean, the magnitude is equal to the positive weight if the number is unsigned. So this number is going to be -16 plus 4 plus 2, okay, which is -10, okay? And if you want to make sure about this, take the 2's complement here. It becomes 0, 1, and then 0, 1, 0. Okay, what is this? It's +10, so this must be -10. Okay? Do you see that? So in general, if you have n-bit number in 2's complement, then the most significant bit is going to be to have so this is bit 0, bit 1, bit n-2, actually big n-2, bit n-1, okay? So this bit is going to have -2 to the n-1, and this bit here is going to have +2 to the n-2, and this one is going to have +2 to the n to the 1, and this one is going to have to +2 to the 0. Okay. All right. So enough of that. So what is the if I ask you what is the in 4-bit 2's complement, what is 1110? Immediately tell me that this equals, in decimal, this equals what? -8 plus 6, which is -2. Okay. So if I add 7 plus 7, do I get -2? No. So this is what is this saying? 7 plus 7 equals -2. That is wrong. Okay. So there is an overflow here. All right. So then we did an example, and we saw that in this example there is no overflow. Okay. So a quick check of overflow, okay, can be done also by comparing the last two carries. Okay, the last two carries. If the last two carries are equal, then you don't have an overflow. If the last two carries are different, then you have an overflow. So you basically take their XOR. If their XOR is 1, this is an overflow. So let's do another example here. Okay, who can tell me what is the value of this number here in decimal? So this is this part here is equal to what? This part of the number is equal to 32 plus 1, which is 33, right? And this part here is equal to minus 2 to the 7, which is minus 128. Minus 128 plus 33 is
minus 95.
28, 33. Yeah, just minus 5, and then 9, right? So if this is minus, then you get the minus 7. So this is minus 95, okay? Let's do the subtraction here, okay? I mean the addition. It's an addition of two negative numbers, right? What about this number here? It's 12 minus 128, right? Actually, minus 128 plus 12. Okay, but I can do the other way around. So this is going to be actually 6. Okay, 6, and then 1, and then 1. Okay, 116. So the answer is negative 116. So this one is going to be minus 116. Okay, all right. Let's see the answer here. So 0 with a carry of 1. Okay, and then 1, and then 1, and then 1, and then 0, and then 1, and then 0, and then 0 with a carry of 1. Okay, you see that? So this one is going to be discarded. However, you can see that this 0 creates a 0 carry here. Okay, since these two bits are different, the last two carries are different, then we have an overflow here. Why do we have an overflow? Because the numbers are the input numbers are negative, whereas the result is positive. Okay, what is the result here? What is the the result in decimal? It's 14 plus 32, which is 46 plus 46. So this doesn't make any sense, right? This is wrong. The result is wrong. Okay. So there is an overflow. However, this is the result that you get out of the addition. Okay. So there is an overflow, and the result is this one. Okay. This one is discarded. This last carry is discarded. Okay. What about now a subtraction problem? Remember, in the subtraction, in 2's complement subtraction, what do we do? So if you have A minus B, what do we do? Who can remind us what we can do? This is A. We convert it to what?
Plus negative B.
Excellent. Plus negative B. And then this is equal to A plus B complement plus 1. Yeah, that's the 2's complement of B. So we need to convert this to the 2's complement, yeah, which is B, and then the operation becomes addition. Yeah, what is the number here? The 2's complement of the number. It's going to be 1, and then 1 0 0, and then 3 1s, and then 0. Anyone not following? And then I copy A as is because A didn't change here. Okay, 1 0 1 0, and then 0 0 0 1. Okay. So I perform the addition here. Okay, so it's 0 with a carry 1, and then 0 with a carry 1, then 1, then 0, then 1, then 0 with a carry of 1, and 0 with a carry of 1, and finally we have a 0 with a carry of 1. Okay, that is discarded. Okay, so the result is going to be this one here. So is there an overflow here?
No.
Answer is no. Why?
The
last two carries?
yes, the last carry is equal to
Is equal to the previous last carry, right?
yes.
So the last two carries are equal. Okay, the last two carries are equal. That's why. All right. Okay, so do we need to double check the result? I'll leave it to you to check the results. Okay, the result of whether this is this minus this equals this. Okay, do it in decimal and then double check. Okay. So moving on. Now we are ready to discuss the adder-subtractor circuit. Okay, the adder-subtractor circuit. Okay.
Doctor,
Yes, I have a question.
when we have an overflow, does that mean we have 9-bit code? The result, I mean.
Yeah. So your question is about how to correct the overflow. This is your question, right?
Yes.
So the result when you have an overflow is incorrect. So how to correct the overflow, we'll talk about this at the end of this lecture, inshallah. Okay. Yeah. Excellent question. So now we talk about the adder-subtractor circuit. Okay. So we have talked about the ripple carry adder before. We can just tweak it a little bit such that it can work for both addition and subtraction. Okay, so we assume first that A and B are 4-bit without loss of generality, of course. And both A and B are signed integers using 2's complement representation. Okay, and we denote the output of the ripple carry adder as S. Okay, so S is a function of A and B and M as well, in which M tells us whether we want to do an addition or subtraction. So M is the mode. Okay, so for when M is 0, we'll do addition, and when M is 1, we'll do subtraction. Okay, so mathematically speaking, my S as a function of A, B, and M is equal to A plus B. I'm not referring here to OR gate. I'm referring to arithmetic addition here. Okay, A plus B if M is 0, or A minus B if M is 1. All right. I mean, I haven't done anything. I just written a definition of S based on M, right? Okay. So using 2's complement definition of minus B, we can rewrite this definition as this doesn't change, but this one becomes A plus B complement plus 1. Okay. Again, this equals this one here, which is from the previous page, equals A plus B plus 0, okay, which is M in this case. Okay, if M is 0. And we can also replace the 1 with M as well, since M is 1 here, right? So in either case, in either the case of when M is 0 or M is 1, we can have a carry N of the adder to be M, okay? The carry N, which is 1 bit, to be M instead of just making it 1 time a 0 and 1 time a 1. So the carry N will program either case for us, okay? All right. Now, what remains is the B or B complement. Okay, so we would like to have a circuit that basically generates B for us if M is 0, and B complement when M is 1. What is that circuit? Anyone remembers? Or gate, in other case, in other words. We have some circuit here, some gate here. Gate. You take A and you get you take M, okay? Actually B, it's not A. B. B, okay? And when the B is 4-bit, by the way. So let me take only one bit of B, because M is 1 bit, okay? And we would like to output B 0 complement when B is 1, and B 0 when B is 0. What is this circuit? What is this gate? We learned a gate like this before. Well, if you do remember, if I have an XOR gate and I XOR B0 with 0, what do I get? Anyone have been reviewing in the past few days and preparing for the exam, which is already too late to do that? Answer is B0. Remember, B0 XORed with 0 is B0. This is a property of the XOR gate. You guys remember that, right?
Yes.
Yes.
You just remembered, or you did remember, but you didn't talk. Make me feel better, please. Okay, what about this one? B0 and XORed with 1. What is the result?
B0 complement.
Okay. All right. So if I replace this with M instead, M can be 0, it can be 1. So this is going to be XORed with M. And when M is 0, it's going to be B0. And when M is 1, it's going to be B0 complement. So this gate is nothing but an XOR gate, okay? So what I'm saying here is that my function, which is S of A, B, and M, is going to be A added with, this is addition, it's not OR, okay? Added with B, and then XORed with M, okay? But we have 4-bit of B, so we have to replicate the bit M 4 times for each one of the B's. Okay, so if M is 0, and then this becomes 0, 0, 0, 0. So you XOR together, you get B complement, okay? I mean B. And if this is 1, okay, if M is 1, this becomes 1, 1, 1, 1. And then you XOR it with B, you get B complement, okay? So this way, we just got rid of the condition, okay? So this is one statement, one big statement, that we can now use the ripple carry adder with some XOR gates and carry N, okay, to implement our Adder-subtractor, okay, where M is our choice of the operation. Okay, you can see here that B0 is XORed with M, and then the result is going to be added with A0 using a full adder. And at the stage 0, we have a carry N of M, okay? So depending whether M, whether we are adding or subtracting, M will be 0 or 1, respectively, okay? And then at the next stage, we XOR M with B1, okay? And then add it with A1 together with the carry N from the previous stage. And similarly for the rest of the stages, okay? Any question here? So this is an adder-subtractor circuit. This is an adder-subtractor circuit. This one here is a ripple carry adder. We have extended its functionality, okay, by including these XOR gates, okay, for B to either generate B or B complement, okay. And also we have extended its function by inputting M instead of just a 0 in the carry N, okay. All right, no questions are there. I'm going to continue discussion. So this is, again, this is an adder-subtractor circuit. So what about detection of overflow in more formal way of doing that, okay? The difficult way of doing it is this way, okay? To check if the sign of A equals the sign of B, and the sign of the result, okay, this is when adding a plus b, okay, and the sign of the result is not, it does not equal to sign of a or sign of b, of course, because they are equal. If the whole thing is true, then it doesn't matter whether this is sign of a or sign of b, okay. Then you get an overflow. Otherwise, you don't get an overflow. When you are subtracting, notice that subtraction is equivalent to this addition here. Okay, so we're testing if sign of A does not equal the sign of B. Okay, and the sign of A plus B, actually say sign of the result. I mean, it should be minus B, okay, which is the result. Okay, does not equal to sign of A. Okay, then you have an overflow. Okay, but this is too complicated to watch for. So again, you can use implications and mathematical deductions, okay, and conclusions to come up with this test for overflow. Okay, if Cn minus 1 XORed with Cn, the last two carries XORed together is equal to 1, which means they are different. Okay, then we have an overflow. Otherwise, we don't have any other overflow. Okay, you can prove this yourself, but we don't have time to do that. Anyway, you can base it on these two definitions and then imply this fact here. Okay. So in order to check for overflow, this is the bottom line here. In order to check for overflow, all you need to do is to watch the last two carries. If they are different, then you have an overflow. If they are the same, then you don't have any overflow. Okay? All right. So now coming back to the question of avoiding overflow. So one of you have asked me at the beginning of our lecture today is how to avoid overflow. Now, we know that overflow, when we have an overflow, the result is wrong. So how to rectify this problem, okay? So first of all, we must check the bounds of the result, okay? And then make sure that our result, okay, can cover the range of the values that we have, okay, in the worst case. But extending the result, okay, is not enough because we have signed numbers, so signed operation. So the result of the result itself, when you extend it, you have to extend also the input to the same size. Otherwise, this is not possible. Okay, so for extension, okay, we have two types of extension: zero extension or one extension, or I mean not. Zero extension and sign extension. And zero extension is used for unsigned numbers, and sign extension is used for signed numbers. So here is an example. If you have 1001, which is 0 extended to 6-bit, okay? The number is already 4-bit. We'd like to extend it to 6-bit, okay? Which is, and we assume that the number is unsigned. So we have to 0 extend it in this case by adding 2 zeros to the left. Okay, so this is a 0 extension by 6 bits. If the number on the other hand is signed and you'd like to sign extend it to 8-bit, then all you have to do is to replicate the sign bit. Okay, if the sign bit is 1, you replicate 4 ones. Okay, if the sign bit is 0, you replicate 4 zeros. Okay, why 4? Because we are extending it to 8-bit and the number is 4-bit, so we need 4 more bits. Okay, here is another example. So we would like to sign extend this number to 7-bit now. Okay, so we write the number itself and then replicate the sign bit, which is 0 in this case, 3 times. Why 3 times? Because the total number of bits becomes 7 as requested. Okay, any question about this? Okay, so note that extending an integer to a larger size does not change its range of value. For example, if we have A that is 4-bit, okay, as an input that is 4-bit and it is signed in 2's complement, then the extended bits of A will only be constant bits, okay, which equals the same bit, okay? So the range does not change for A, okay? If you sign extended, you're just making it more, you're increasing the width of A, that's it, okay? You're not increasing the range of A, all right? Also, we can show that this does not change the value of A. So this one here, for example, in this example, if this number is signed, okay, what is the value of this if it is signed in 2's complement, by the way? What is the value of 1001 if it is signed in 2's complement?
Minus 16.
Okay, that's one way. One say. Who have another say in this? N is 4 here, right? So we have -2 to the 3.
Yes, -8. Yes.
Plus 1, which is -7. So this number is -7. Okay? What about this number here? All I'm saying is that the sign extension does not change the sign of the number. Okay? So this is going to be the positive part of the number. Okay? So what is that now? It's going to be so this is 16, 32, 64, 32, 16, 8, and 1, right? But we have a negative, what? 128 plus, okay? So this becomes what? -64 because they're half of each other. And then this becomes -32. And then this becomes -16, okay? And this becomes what? -8, okay? And then becomes -7. It's the same, okay? Do you see that? So there is nothing to, I mean, the sign extending the number doesn't change its value, okay? Sign extending or 0 extending in the number doesn't change its value. All right. However, it helps us avoiding overflow in the output, okay? It helps us avoiding overflow in the output because it increases the range of the numbers in that we can represent in the output, not in the input, okay? All right, let's take an example. So here we would like to design a circuit that outputs x plus y, where x and y are signed 4-bit, and we would like to avoid overflow as well, okay? So for this, we need to find the range of S and then decide on the number of bits of S. That will give us a clue on what is the extension required for X and Y, okay? So the max S is what? Is when X and Y are positive and maxed, okay? So the maximum number for maximum positive number when you have 4-bit, it is 7, right? Plus 7. Plus 7 plus 7 is plus 14, right? This is the maximum value of S. The minimum when both are negative. So when both are negative, it means -8, which is -16. So we have the range from -16 to plus 14, okay? And this is covered by this range, which is -16 to plus 15, which is -2 to the 4 up to 2 to the 4 minus 1, right? So my N is 5, okay? So we know that 5-bit is the range, okay? So we need to extend A and B to 5 bits instead. So do we extend them using 0 or sign extension? I mean X and Y, not A and B, okay? X and Y. Do we extend them using 0 or sign extension? Allah understand. They are signed, okay? The numbers are signed. So do we extend them using 0 or sign extension?
Sign extension.
Okay. Yeah, that is correct. We need to extend them using sign extension. So X becomes what? X3, because we just replicated the sign bit, okay? And then X2, and then X1, and then X0. And Y becomes Y3, and then Y2, Y1, Y0. And then we need to add the two numbers, right? Just add the two numbers using a ripple carry adder, okay? So we have a full adder here that has an input carry of 0, and it takes X0 and Y0 and to produce S0, okay? And then propagate the carry out to the next level, which is X1 plus Y1, all right, to produce S1, and so on and so forth. But note here that we have replicated or sign extended the number to 5 bits, okay, or to 4 bits. I'm sorry, 5 bits. Yeah, 5 bits. Yes. So note that X here. We have Y3 and X3. Here we have Y3 and X3. This is the sign extended bit, okay? And this produces for us S4. So using this design here, you can never get an overflow, okay? You can never get an overflow. And this means that this carry out will always equal to this carry out, okay? Will always equal to this carry out, okay? You can basically prove this mathematically if you want to. All right. Is this example clear?
Yes.
Okay, let's move on to the next example. So we would like to design a circuit that computes X minus Y, okay, again, avoiding overflow, and X and Y are 4-bit unsigned now. They are unsigned 4 bits. So X goes from 0 to 15, and Y goes from 0 to 15, okay? Now we find the maximum and minimum of S, okay? So the maximum is going to be 15 minus 0, okay? Which is 15, or plus 15, okay? S is signed, okay? S is signed, but X and Y are not signed, okay? And minimum of S is going to be 0 minus 15, which is minus 15, okay? So what is the range? It's from minus 16 to 15, so you need 5-bit again, okay? 5-bit for S. So we need to extend X and Y to 5-bit rather than 4-bit. Do we use a sign extension or 0 extension here?
0 extension.
Excellent.
Because sign.
Because the number, the input is, or the inputs are unsigned. Yeah, so we use 0 extension here. Okay, which means that the inputs are always positive. Okay, they're not negative. So we append the 0 to their left. So the problem becomes like this. So my S is equal to 0 concatenated with X, right? X is 4-bit. With this 0, it becomes 5-bit. This becomes 5-bit. Minus 0 concatenated with Y, right? Now using 2's complement, I can convert this subtraction to addition problem, okay? So this is 0x plus 0y complement plus 1, right? And this becomes 0x plus, now I can put this complement this 0 to become a 1, and then take y complement here, okay? And then add 1 here, okay? So this is my carry in now, okay? And then I'm adding y0 complement with x0 and y1 complement with x1, and so on and so forth. But eventually I have a 1 plus 0. You see that? 1 plus 0, or a 0 plus 1, right? So x plus x0 plus y0 complement, and the carry in is 1 initially, okay? and all the way to the final one, which is 1 plus 0, nothing but 1, or 0 plus 1, which will produce for us is 4. And by contracting this design here, or design by contraction, remember, what is this 4? Is 4 is nothing but the XOR of these 3 inputs, okay? If you XOR them, you get C4 complement. So this is nothing but an inverter here, okay? And also by the same method, you can get the carry out here, okay? The carry out, if you want to make sure that the result is always doesn't generate an overflow, you'll find that the carry out here is going to be equal to C4, okay? So C4 XOR to C4 is always 0, okay? So there will never be any overflow, okay? Any question? Let's move on to the next level of examples, okay? So now we would like to implement a circuit that implements S that equals 2 times X plus Y, where X and Y are signed bit, okay? So what is the maximum S? Maximum S is going to be 2 times plus 7. X and Y are signed 4-bit, okay? And using 2's complement, plus 7, okay? Do you see that? And the result is going to be plus 21. And the minimum S is going to be 2 times minus 8, okay? You must know the range of 4-bit. Okay, the range of 4-bit is minus 8 to plus 7, okay? Plus minus 8, which is minus 24. And this range here, minus 24 all the way to plus 21, is covered by this range, minus 32 to plus 31, which means you need 6-bit, okay? 6-bit, because basically this is minus 2 to the 5, okay? So your n minus 1 is 5, so your n is 6, okay? So mathematically speaking, my S is going to be 2 times the concatenation of X3, X3, and X. So I'm sign extending X to 6-bit here. So I need to replicate the sign bit by 2 times. Why 6-bit? Because I need the output to be 6-bit in order to avoid the overflow, okay? So sign extending the X to 6-bit here, and sign extending the Y to 6-bit here. You see that?
So, Doctor,
Yes.
if we make it a 5-bit, the range will be smaller than minus 24 to 21.
Yes.
That will cause an overflow.
Yes.
Okay.
Yeah. So basically, the minimum rate, the minimum that you can pick is 6. You can put it 7 as well, but you will have redundant bits. Okay. But the minimum range is from minus 32. So what is minus 32 now? Minus 32 is minus 2 to the 5. And you know that 5 is equal to n minus 1 in your case. So your n is going to be 6. Okay? You
Yes.
see that? Okay.
Yes, yes. It's clear.
Yeah. So you have here multiplication problem, okay? Multiplication by a power of 2. Remember, when you do multiplication by a power of 2, what do we do? So you have 2 to the n into a binary number, which is 101, for example. You'll have 101, the same number, followed by how many zeros?
N zeros.
N zeros. N zeros, exactly. No, not n minus 1, okay? So we have 2 here times x3, comma x3, comma x. So this will be equal to what? First of all, we have if we can this is the result here. It must be 6-bit, by the way. Okay, so we cannot exceed 6-bit in this case. In this case here, we are assuming here unlimited or unsigned numbers, but for signed numbers, you have limited number of bits. So you will have to shift the number to the left with the most significant bit lost. Okay, so you have x3, okay, and then followed by this one here. This one will go, okay, and then you'll have to add a 0 here. Do you see that? So x3, then x, then 0. This is the result of the multiplication by 2. All right, so here I'm using it, x3, x, and 0. You see that? Plus y3, y3, and y. This didn't change. All right, now this tells us that I'm adding y0 here, which is the last bit, the least significant bit of y, with 0. Okay, so the first full adder adds y0 with 0, with a carry n of 0 to get y0, to get s0, which is nothing but y0. So my first s0 is nothing but y0. And then y1 will be added with x1, with x0. You can see that. And then y2 will be added with x1. This is because of the shift operation that we did, okay? And eventually, at the end, we have the same bits. These two bits are going to be the same, okay? So these are the 6 bits of the result, and you can never have an overflow here because this carry here will be equal to this carry here, okay? Must be. All right. Any question here? Well, let me stop recording. We will continue next time to discuss the unsigned less than operation, okay, which is, we'll use subtraction to implement that, okay. But for now, let's stop here and continue, pick up from next lecture.